All right, so continuing on, if we take a proton and release it from this 1.5 volt plate and it goes over to the 0 volt plate, it's going with the electric field, positive to negative plates, and that makes sense because a positive charge, like a proton, is going to experience a force in the direction of the electric field, and it's going to accelerate, and it's going to gain speed, and it's going to hit this negative plate with some speed, and that speed came from the potential energy that it had due to its position in the electric field at the start. Just like releasing a ball, gravity pulls it down, energy that was in the gravitational field gets converted into kinetic energy. Here, energy in the electric field gets converted into kinetic energy. So we use conservation of energy. It is important to note that when you start at 1.5 volts and go to 0, you have gone down in voltage. So delta V would be a negative there. So if we use conservation of energy, at the beginning we only have electrical energy, and at the end we have electrical and some voltage. This would work whether your voltages are, like I said, 1.5 and 0, or whether they would be 8.5 and 7, or -3 and -4.5. So you could just plug in the voltages right here that you know, or you can find delta V, and remember delta V in this case was negative. That's going to cancel off with this negative. Continue here, plug in the numbers, and find the velocity. It's going to be something on the order of 10 to the 4th. Oh, and then over on the right, use this space to answer the second part of the question. What would happen if the plates were separated by 3 centimeters? Did anything in here involve distances? No. So that should be a hint. Also, when you increase the plate separation, that will affect the electric field between them. It makes the electric field a little bit weaker, but a weaker electric field will put less of a force on the particle, but you're also giving it more distance to accelerate. So it's going to reach the same speed at the end. All right, so there's a trade-off either. That's not really a trade-off, but if the plates are really close, you have a strong electric field, the particle experiences a big force and a large acceleration over a short distance. When the plates are separated further, you have a smaller electric field, so less force, but a greater distance over which to accelerate. In the end, they're going to have the same speed, because what's important is the difference in voltage, not how far apart those points are physically in terms of energy. The potential difference required to stop an electron. If you're going to stop an electron, the electron wants to go with the electric field. Sorry, electron wants to go in the opposite direction of the electric field. So an electron wants to go to areas of higher voltage. That's what it would do naturally. It gains speed when it goes to higher voltage because potential energy is converted into kinetic. The electron needs to go with the electric field to experience a force in the opposite direction. So we start off with kinetic energy, and we start at some initial voltage, and we're going to end at some final voltage. You're going to figure out what is delta V. It should be negative. Would a proton require more or less voltage to stop? What about a neutron? Proton would need more since it has more energy due to its speed. Neutron doesn't experience electric forces, and no amount of voltage will stop a neutron. So you're going to use work similar to what we have up here to show that result. Use special case number 1 from earlier in the notes to show these results. We did this in class. The electric potential due to an arrangement of charges. Use superposition. Add up the individual voltages to find the net voltage. And if you're working with potential energy, then you have to figure out how much energy exists between each combination of two charges in the configuration. So each pair of two, and like pairing up 3 and 2 is the same thing as pairing up 2 and 3. So we don't want to double count those. So you don't count repeats in here. And the U's here represent the energy between the two charges. So take a look at this diagram. We have 3 charges right here, right? 1, 2, 3. If we want to find the voltage at point P, which is one of our tasks, we can just use the individual voltage. What's the voltage at P due to charge 1? What's the voltage at P due to charge 2? What's the voltage at P due to charge 3? Add those 3 voltages together at point P to find the net voltage there. Superposition. For the potential energy, for these 3 charges here, I need to find the energy associated with each pair of 2. That means these 2, 1 and 2, 1 and 3, and then 2 and 3, right? 3 charges, and we can make 1, 2, 3 sets of 2 out of those 3 total. So, very straightforward. R12 is the distance from charge 1 to charge 2. R13 is the distance from charge 1 to charge 3. So, you show the work in each of these cases, come up with a number. Now, if we take that same example right here, and we're going to bring in a 4th charge and put it at point P. Finding the voltage, now it says find the voltage in the middle of the arrangement, okay, right there in the middle. All 4 charges are equal distance away. Okay, you can figure out what distance that is. And then you're just going to add up the voltage from each of these 4 charges at the center. Okay, show me the work, you'll get 7.2 times 10 to the 4th, or close to that. The potential energy will change by the amount of work required to bring in this 4th charge and put it at point P. So when you bring in this 4th charge, you have to do some work against this charge, and this charge. This charge is creating an electric field, and we need to figure out how hard it will be to bring in this one against that field. How hard will it be to bring this against that field? How hard will it be to bring this against that field? So the change in potential energy is equal to the amount of energy that this has in relation to each of those 3. So that's what you'll be finding. It's going to be about negative 0.207. Show me the work there. And the last thing that we will discuss is a relationship between electric field and electric potential, relationship between electric field and voltage. The way that you'll most commonly see that in Physics C is E equals negative dV dx, and that would be in the x direction, in the positive x direction. It's the negative slope of the voltage function. Just like force is negative slope of potential energy, the electric field is the negative slope of the voltage, because voltage is energy per unit charge and electric field is force per unit charge. So it makes sense they have the same kind of relationship. You could do this in each dimension. Multivariable calculus, not part of physics C. But if you did this in each dimension, you'd have a full version of the voltage. And taking that set of negative partial derivatives with respect to each dimension has a special operator in math called the del operator. And that's used to find things like divergence, gradients, curls. In vector fields, you don't need to know what those are, but maybe you'll remember hearing about them someday. So there's just a little example here of how you might do a partial derivative in each dimension, right? Differentiate this with respect to x first, then with respect to y, then with respect to z. You won't really find examples like that. I just included it in here for a little extra. If the electric field only exists in one dimension, then it's just negative dV dx. And I gave you one quick little example there. That's going to be it. See you